Can you see my screen?
Yes, sir.
Yes, sir.
Okay. Okay. So far we have looked at some basic terminologies in communication, and we have looked at the transmission media types, just some basic definitions, properties, and so on. And as I have noted, most of the communication things will be taken care of for you. The media thing, you need to know the properties and all to choose one properly when you're designing a network. We looked at a small example, and when we do more things, LANs, switches, and so on, so we'll kind of expand that a little bit slowly. So what we will start today is this simple thing. Forget about a large network. I just have two machines connected by a link, okay, one of those medias. So what all do I need to ensure reliable data transfer between those two things? So think about our lab yesterday. You think about those two things, opening sockets and connecting. So I don't want in order, but I want reliable. And the assumption that I make is that these are directly connected by one link. Nobody else is sharing that link. Nobody is just going to interfere. So only these two machines communication going over that link. So the idea is that if I do not know how to make two machines communicate, I definitely do not know how to make more than two machines communicate. So your scaling up is in terms of number of machines and the number of links. Okay, that's what the complete network is. It's a graph with lots of nodes and lots of links. So we'll first look at only two machines, one link. Then we'll see one link. We don't scale up on the link, but what if more than one machine share that link? How do I ensure that sharing and so on? So I still have one link, but I have more than one machine. Okay, which will be kind of the basis of LAN. And then we'll look at the more general case, the broader internet, which is any number of machines, any number of links. Okay. And this one also, I'll point out again, summarize at the end after I've done everything. This is probably going to take us at least this week with the extra class. So some part of it will be done by hardware on your network interface card. Again, somebody has to build that hardware. There are algorithms there also and so on. So you may work in that. Okay. But then some part will be, you will have the genesis of things which have, which you will see in software also a lot. Okay. So we'll point out basically what is the status at the end of that thing. But let's learn the concepts. So what do I need to know, or what problems do I need to solve, okay, to make these two machines communicate? So first is, how does the receiver know when the sender is sending data? So each of these points we'll look at in more detail. So that's what this entire set of slides are. So right now I'm just going to quickly say this. Okay. So how does the receiver know when the sender is sending data? So I need to kind of tune my receiver to start listening. Okay. When you send data, see, my ear is always on. So if you say something, my ear picks up. But think of a circuitry which is kind of turned off, and then it has to be turned on, knowing that you are going to send me something. And then you are going to send me something at regular rates. So I need to kind of listen at the regular rates and so on. So we'll see what the issues are. And then encoding. We have said that represent data with signals. What are the techniques? I want to send a bit stream 1010. How do I encode? I said that I will encode with signals, but how do I encode? And then actually we'll do them in different reverse order. So flow control talks about this. So flow control and error control is the basis of all networks out there, or TCP/IP networks out there. So flow control says, how do you ensure the sender does not swamp the receiver? If you speak too fast, faster than I can grasp it, okay, I will not be able to understand it. I will not be able to retain everything. Okay, but these are two machines that decide that they will communicate, and the sender sends very fast. The receiver cannot process it that fast. So how does the receiver let the sender know, don't send it, what are the techniques and so on? So they come under the purview of flow control. Whereas error control says, how do you ensure the receiver gets the correct data? As we have seen, for many reasons, like noise, attenuation, etc., signals can get distorted. Therefore, a 0 can become 1 with noise, 1 can become 0 with attenuation. Okay. So when it reaches the receiver, how does the receiver first of all know? How does it detect that it is sensing a 0, but probably there is something wrong with it? Okay. How do we detect that? And then what do we do on detecting to ensure that eventually the receiver gets the correct data? So when I talk about communicating between two direct machines, these are the issues that we need to know about, and we'll look at each of them in detail. Somewhat detail. What is the need for synchronization? Okay. So to understand that, you need to understand what happens basically, not the underneath circuitry and everything. So transmitter just sends a stream of zeros or ones. We'll answer the question when, but think that the transmitter is sending and the receiver is listening. So the receiver, what happens, it will sample the incoming signal once per bit time. So there has to be a notion of a bit time agreed between them. Okay. I should know that you are going to send me at 100 Mbps. So I know what the bit time is. Okay. 1 by 100 M basically. So what the receiver does is, suppose it syncs, suppose here they are at sync and it says, this is where the sender will send me the first, start sending me the first bit. So this picture is slightly off, you could have done anywhere. Okay, anything is done. So somewhere between this bit time, they're going to, the receiver going to sense. If it finds whatever corresponds to a 1, it will sense a 1. If it finds whatever corresponds to a 0, it will sense a 0. Okay. This is typically at the center of the bit, but not necessarily so. And we'll see there are other techniques also. Okay. So that's how basically basic receiver samples the bits, because it knows, it has to know a priori agreement that what is the bit time. Somehow the sender has to tell that this is the bit duration. Okay. This can be a priori agreed that we're operating at 100 Mbps and so on. Okay. And then if it knows that, if it knows where to start, it just sense like, this is 1, this is 1 microsecond. So I'll sense after 0.5 microsecond. So every 1.5, then 1 microsecond, 1 microsecond, 1 microsecond, 1 microsecond later, I'm going to sense it. And whatever the voltage level I find, depending on what it is, the receiver says is 0 or a 1. So that's the basic thing. Okay. So just illustrating that little bit more. So the transmitter sends 1 bit 0 or 1 every 1 millisecond. That is too slow actually. Okay. But let's just assume the 1 microsecond would have been at least somewhat. But anyway, so say there is a clock that ticks every 1 millisecond. So transmitter, what it does, it puts a 1 or a 0 on the line at each tick of the clock. Okay. So if I look at the transmitter, okay, so this clock is ticking, and then when it ticks here, and is 1 microsecond, the receiver will say, okay, let me put, suppose 0 is this high, let me put for this 1 millisecond. Just start here, hold the line for 1 millisecond, put it down. Okay. The next clock tick here, 0, fine, let me do a 0. Next clock is 1, let me do a 1 for 1 minute. Next clock is 1, let me hold the 1. We'll see this will vary with the encoding, but let's just assume that simple 0, 1, high and low thing. Okay. And so on and so forth. Okay. 2 zeros will be like this and so on. So okay. Now, first of all, the receiver needs to know when to start counting. From where should it start looking, so that it knows from where to start that middle. Okay. So it needs to know that this is where the first bit, because the receiver is just lying there. Okay. And then it needs to know when to look for the next successive bits. Okay. Now, here is the problem. So suppose all this is agreed, it knows when to start looking, and it knows basically that this is 1 millisecond. Okay. Again, 1 millisecond is just too slow, basically, but it's okay. So think of the bit stream coming like this. Doesn't matter what it doesn't need to be alternating. Okay. So each of this is 1 millisecond, just suppose. All right. Then the receiver samples here. Okay. But then the receiver and the transmitter clock need not be exactly synchronized. Okay. So let's say the receiver runs like 1% slow. Can be anything. Okay. Which means what? The transmitter is sending every 1 millisecond. Suppose the transmitter's clock is perfect, whatever that means. The receiver's clock with respect to the transmitter is 1% slower. So its 1 millisecond as per the receiver's clock will happen 0.01 millisecond later. So first time, let's do this. Just couple of things very clearly. First time, say it does here. Then the next bit interval was supposed to happen here, but it happened slightly later for the receiver because its 1 millisecond is happening a little slower than the transmitter's 1 millisecond. So it'll shift a little bit from the middle. Next one, the same thing will happen. If this is the transmitter's thing, it's already starting late and this will be slightly more later. So this gap will increase. Okay. So now you see where I'm getting at. If I let this continue, this clocks to be 1% slower and continue, okay, then eventually what will happen is this receiver sample thing will fall off here, and while it wants to sense a 1, it will actually sense somewhere out here. So this 1 will be completely missed and it will sense a 0. And then it will think that this is the 1 0 bit. So eventually it will miss a bit also. Are you with me? This is crucial to understand. Even when we do encoding, okay, we'll see this will be one of the goals. You have to be synchronized. So very simply put, the way the receiver knows about the bits is going to sample at specific times. What is the time? The times at which the transmitter is supposed to send out the bits. But in the middle of the interval, not exactly at the edge, because edge may get corrupted a little. Okay. So it senses in the middle, but then if 1 millisecond of the sender is not the same as 1 millisecond with the receiver because their clocks are slower or faster, okay, then what I think is 1 millisecond at the receiver, okay, will be slightly, in this case, slightly larger than what the transmitter thinks is 1 millisecond. So transmitter is put thinking this is 1 millisecond, half of that point here, but I will sense a little bit more than half a point here. And then this thing will keep on adding up and eventually I will drop a bit. Are you with me? Yes, no?
Yes, sir.
Okay. So I need to do some way the clock synchronization between sender and receiver. Okay. I need to keep their clocks synced. I need to let them know when to start counting, and I need to know when their clocks sync. Okay. Now this knowing when to start counting, okay, is, I'll not go into details, but you have circuitry which can be triggered by a pulse, okay, by a change in the line basically. So the idea is basically I will keep, when I'm not sending anything, I'll keep the line at something, okay, and then I can design a circuitry. So the receiver is just waiting there. It sees that voltage, it knows there is nothing, and then it triggers something else that will trigger the circuitry to say, oh, now there is some transmission starting. So that part is not very difficult. Okay. But then this clock has to come because I just know the transmission has started because the pulse has come. Okay. But then I need to know at what rate is the sender sending these bits. So there are two possibilities. Okay. The rate has to be known a priori, but then whether my clock is running fast or slow or something that I have to synchronize somehow during this transmission. And there are two ways of doing it, but before I do that, we'll start introducing a term. Now we're getting into networks proper. It's called framing. Okay. So typically when you send things, you will not send one continuous large thing in ad infinitum, 0 1 0 1 0 1 0 1 and so on. You will break the pattern up typically into multiple frames. Okay. And you will put some identifier plus some other things on each frame to distinguish between frames. Okay. We'll see why they are needed. And then, so now what I talked about is bit synchronization thing. I also have this frame synchronization problem, thinking that when does a frame begin and when does a frame end. So let us look at the techniques, we'll understand it better. If not, we'll come back to this again. But think about that now. So far we have been talking as just a bit stream, as if it's like ad infinitum bit stream. But now you think about, I'm sending frame by frame. The sequence of bits together can be any pattern of 0 1s, okay? Then nothing, then 0 1s again, a frame, then nothing, then a frame again, and so on. That's how communication underneath happens. So we have noted already synchronization is needed, and we talk about two types of transmission, asynchronous and synchronous. Okay, so these words asynchronous and synchronous are two of the most heavily loaded words in computer science. They are used for many different things: synchronous this, synchronous that, asynchronous this, asynchronous that, and so on. Okay. And in this context, asynchronous is a little bit misnomer. Okay, in the sense that asynchronous means lack of synchrony between transmitter and receiver. Okay, it's not that really, but we'll see what this means. Okay, so what I'm trying to say that you still need to sync. Okay, but the way the syncing happens for asynchronous and the way the syncing happens for synchronous is different, basically. So what is asynchronous? Okay, so basically it states a transmitter and receiver has separate clocks. Okay, and then the data rate and frame format is negotiated up prior. Frame format is always known up prior. That doesn't mean the exact size is not up priori always, but the format is always known up priori. I will first send you this, then days, and so on. As we go on, this will become clearer and clearer. And what I do is, so basically when there is no communication, okay, so separate clock means when no communication, clocks run at their own speed. So I don't try to make it, okay, or even, okay, whatever. So you get the idea. The idea is that you have to just try to visualize with me, okay. So you have a transmitter and a receiver. They have their own clocks, okay. They're running at their own rates. But I know at the receiver end that if the transmitter sends me data, he's going to send me 1 megabits per second. So 1 megabits per second. Okay. And this frame will be like this. There will be a start bit from this. This is my idle thing. So there will be a start bit where there will be a change. Then there will be 5 to 8 bits of data. Okay. Then there will be a parity bit. I'll explain what it is. And then there is a stop bit, which is another change. Okay. So you want to maintain the timing of synchronization only between this one character. Okay. Now why does clocks go bad? Okay. The clocks go bad because there is a drift. So no two clocks are the same. If you know about clocks, basically underneath there is a crystal that is oscillating in your PC. Think about your PC clock. Okay. And this sort of every so many oscillations of the crystal, there's an interrupt that occurs. That's the clock interrupt. And then there is a small software program which says updates the software counter, and then you map it to your day, week, etc., etc. So, okay. But these two crystals, if you buy, they are cheap crystals, and they don't necessarily oscillate at exactly the same speed, even though they are quite accurate. Okay, so it's not that they will go bad every 1 hour, 2 hours, or something, but over a period of time they can go bad. Okay, so there will be a drift. Okay, so the clocks may drift over time basically. So the idea is that I use the start bit to synchronize. So this is the one that I'm sending you to say, you start here, look for this transition, look for this one, okay, and then you basically get what the bit duration. You know, this is what the transmitter thinks is the bit duration. Okay, so synchronize your clock here, then use that to do this thing. Your clock may drift again, but then since I'm doing it every 5-8 characters only, between that time the drift is not going to be too much. Are you with me? So this parity bit is just an error bit, error detection bit. I'll talk about it later. But the idea is basically that I use the start bit to start the clock at the other end, counting duration of that start bit to basically synchronize, and then I just continue with that duration for that long. Now again, your clock may be slightly slower, but then you are not, see that 1% slower thing that I mentioned, okay, for it to drop off at the end of something is going to take a lot of bits. If you take 1% slower, okay, it's going to take like, you know, if it's half a second or something, half of that millisecond, around 50 bits to drop off. So I'm not allowing it to go up to 50 bits. I say very short frames, okay, drop it, that is over. Next one starts afresh. Again, you synchronize that this is where my start is. Are you with me? Yes, no?
Yes, sir.
Okay, I'm a little bit off here. Okay, I don't think this I put it exactly rightly. So the idea is this. Okay, this is important to understand. So this, if you start at the same point, then 1 millisecond, 1 millisecond, 1 millisecond, 1 millisecond. The problem was the transmitter's 1 millisecond may be smaller or larger than the receiver's 1 millisecond. Now, for this to affect the entire thing, okay, it's going to take a lot of time, because the small things will have, instead of center, you will go a slightly here, slightly here, slightly here, but it still take you a lot of these bits to drop off actually and actually misread it. I'm just saying I'll start you at the synchronize at the same start bit, and I will not let you go all the way out there. I'll send very short frames. And the next one will start with synchronizing here again. I'll start the circuitry here, count rate, data rate is known. So receiver will count 1 millisecond, 1 millisecond, 1 millisecond, and so on. Start bit may not have a transition here. That's what I was slightly wrong. Okay. So that will depend on the encoding and what bit is sent here and so on. But the first bit I will ignore. Okay. But that is something that I'm going to use to synchronize my clock, basically. Not ignore, I will take it as the synchronization bit. And the stop will tell me when so. So start tells me when the frame starts. That's the frame synchronization problem we are talking about. Stop tells me this is where the frame ends. When the frame starts, I start counting that 1 millisecond, 1 millisecond, 1 millisecond. Okay. Fine, if I am allowed to go a long way, I may have dropped off, but I'm not allowed to go a long way. The frame is short. So within that time, if I even have a little bit off, it doesn't really matter. Okay. What is the problem with this bit thing? So suppose this is 8 bits. This data is 8 bit. Ignore the parity bit, including parity bit. Suppose it's 8 bits. Parity is for another reason. It's typically there, so I put it here, but nothing to do with synchronization. So think about, I want to send a file, and this is the mode of communication that I use. What is the problem here? Problem is not synchronization. Synchronization problem I've solved. I use the start bit to synchronize, beginning of frame, start counting here. Don't allow the frame to go too long. Stop bit says stop. Then I watch to wait for the idle line. Then again the start bit, idle to non-idle. Tells me this. Yeah. Anybody? Anybody sees anything? So think that I want to send like a 1 megabyte file. So I have to send 8 megabits anyway, right? But then for every, even if I ignore parity, for every 8 bits of that, I'm putting 2 additional bits. So if I look at the line, okay, so this is the crux of line efficiency. If I look at the line, okay, ideally in the utopian case, I want to use the line only to send my data bits. And if I have 8 megabits of data. I want to send them as soon as I want as soon as I can over the line. Okay. But then that will never be achieved. We'll see. We'll have to put other bits in there, control bits. But in this case, it's basically if every 8 bits, 2 bits. That means after every 10 bits, only 8 bits are data, even less than that because of parity, maximum 8 bits, and 2 bits are wasted. That means I'm doing a 20% loss over this. So when I want to send very short things, it is okay. But when I want to send a log file or something, asynchronous transmission is not a very good idea. Simply because the percentage of overhead is too much. So it's a nice thing to know, but if you look at modern day computer networks, okay, you use mostly synchronous transmission. So synchronous says that I will assume that the receiver clock and transmitter clock is synchronized. Okay. So this is one thing I mentioned something slightly wrong. So I want to again, I've already corrected it, but again want to make this very clear. So in this case, the transmitters and receivers clocks can run completely at separate speeds. Okay. Only thing I'm saying is you indicate when to start counting, and you know that I have to do every 1 millisecond. So according to their clocks, they will do 1 millisecond, 1 millisecond. But I will not try to bring those two clocks together. Okay. I'm just ensuring that those drifts that are there, they don't take place, affect me too much by keeping this short. Okay. I know when to start, when to stop, and short frame, so the drift does not affect me too much. Unlike that, in the synchronous transmission, I want to synchronize my receiver clock with the transmitter. So I want to say that what the receiver thinks as 1 millisecond is the same as the transmitter 1 millisecond. Okay. So I will basically want to say that fine, suppose there is no communication, suppose you have drifted apart, but somehow you should be brought together when I communicate to indicate this 1 millisecond, what I think is kind of same as 1 millisecond. Okay. So what I do, we'll look at these things. A block of bits is transmitted in steady stream. So there is no start and stop codes. Okay. But we'll see there are other codes. But we'll see that we pack in more data out there. Okay. So that code is kind of, so the start bit was to start your clock circuitry. Okay. So this block is arbitrarily long. Now I don't care about the drifts. Okay. But then if the block is arbitrarily long, so suppose there is something in the middle, something in the end, we'll see what these are. Okay. And then I send a large number of bits. Then this problem that we have seen can happen. So first one is sends slightly off, next one is slightly off, second one slightly off. If I don't do anything else, this problem can happen. So to prevent this timing drift, I need to send the clock signal from here to here somehow. That's the interesting thing. So just try to visualize with me. Okay. So I can just think that other than this data line, it is a separate line, just logically think. Okay. So data is being sent whatever data, and this one is just sending the clock pulse from transmitter to receiver. So every time a pulse comes, the receiver pulse clock gets synchronized with it basically. So it knows that this is the bit beginning of the bit timer. Okay. So now I need another level of synchronization to allow the receiver to determine the beginning and end of the block of data. Okay. Note that earlier it was not, the start bit was just 1 bit. Basically, I will, I know this fixed frame rate thing. Okay, so I know this 1 and then this and 5 to 8 bits fixed and then stop bit. So I'll start counting. I'll start my circuitry there. I look at the start bit, 5 bits, so fine. 5 bits, parity bit. I know a stop bit. I am expecting a stop bit there. So it's a very fixed length frame for it. Okay. Whereas when I look at synchronous, when we do Ethernet, for example, you will see these data bits can be variable also. The format is fixed, but the size may be variable also. So if size is variable, I need to know where does it end, basically. And therefore, when does the next frame begin? because this just complete bit sequence now, because I'm sending a long bit sequence. Okay. So I need to put something for the preamble, a postamble, but then very, very important is that I need to somehow send this clock over there. Okay. Now, what do you think? Should I send the clock with a separate line?
No, sir.
Why not?
So because then that itself is a line that will present its own problems.
Exactly. First is cost, and the second thing is, as you have said correctly, that is also a signal. So that will again have delay distortion and all those things basically. Okay. This again you are basically sending a discrete pulses. Okay. So I don't want to do that. That's where the encoding comes. Okay. So I'm going to somehow send these clock things encoded with the data. Note that I don't need these clock things at every bit interval here. I don't want the drift to be too long. So before it falls off that edge of the bit, if I can bring the clock together, I'm okay. So it's okay if I send it every 3-4 bit times, every 5 bit times. I don't need to send it every bit time here. Okay. So one of the goals when we do encoding right after this of a good encoding technique, okay, is to see whether it does provide me with that clock as part of the encoding, as part of sending the data. Okay, we'll look at that. This is why I'm harping so much on this one, because this synchronization thing is important. And when you learn encoding, one of the major things that we look at encoding is, does it provide me that clock? Because if it does not, then I cannot do synchronous transmission. And if I cannot do synchronous transmission, okay, then I overhead is too much for sending large data. I want to do synchronous transmission in today's computer networks. Okay. So let us quickly finish off with synchronous transmission. So typically it will say an 8-bit preamble, then some control fields. When we do Ethernet, we look at them. This will depend on the protocol. Okay. So one of them, for example, will be the frame header, frame address, etc., etc. We'll see what this is. This is the major data field. Control fields 8-bit postamble. So this is my beginning of frame indicator. So I look at the line. When I see this thing, I'll indicate this is beginning of frame. Okay, it's not just one pulse. One pulse, basically the idea was to start the clock, start counting. Okay, but I look for a pattern as a beginning of frame. Then control fields will vary with the protocols. Then I will have a long arbitrary sequence of data fields. Okay, usually we'll have some maximum size, etc., but it can be variable. And then a postamble, say end of frame. So that will be broadly the frame format of any synchronous transmission. When I do Ethernet, I'm not going into too much detail of this. We'll actually look at what the preamble, what the thing is, and so on. So Ethernet basically uses synchronous transmission. And then when there is no frame sent, so now what happens here? Okay, so I send the frame and I said, fine, send the clock somehow. But then if I don't send anything for a long time, then the clocks will again go off here. Now, if you start with a clock that is instead of 1% slower, that is 50% slower, okay, then your falling of that bit end will happen much faster. So you send some special pattern in the middle. This is like a clock, but using the same line, not a separate line or something. If you don't send data for a long time, typically in synchronous transmission, you will send some special interframe field pattern, maintain the synchronization. It's like kind of sending your clock periodically, sort of. Okay. Are you okay with this? So the main problem, so the way you need to understand this is that the main problem was that falling off that end of the bit. If I just do not do anything, okay, start I can indicate. I will just start that pulse. Okay, but then if I do not do anything, then if I send a long sequence of bits, every bit instead of the middle, it may go a little bit of, slower will go on the right, faster will go on the left, and eventually you may miss a bit completely. That was the problem. So what's your solution? One side asynchronous says don't try to kind of synchronize the clocks, let it run slow. But then you use the start bit to start them saying that this is where the data starts. So it starts listening from there. Okay. And then don't send a long pattern so that even if there is slight drift, it's not going to fall off the end. But then you have to send a start bit to indicate that this is the start bit and hold it for some time a priori rate and then stop bit to indicate this. But then the problem is a lot of overhead. You want to send a lot of data with a single synchronization. So you take the synchronization out, you say that somehow they are synchronized. They will not have that drift. If they get too slow, I will bring it back. Okay. So I can send a long stream of data. So now I'm sending in frames, and I still have to say what is the beginning of frame, what is the end of frame. That is my preamble and postamble. And then the clock this to bring this together. If it drifts, the clock I can send separately, which is almost never done. Okay, in computer network communication. But then I will do this in the encoding. I'll send my clock somewhere in the middle, may not be every bit time, so that the receiver knows, oh, this is the middle of the bit. So I'll bring it back to say, oh, this is the middle of the bit. So bring its clock back to that middle of the bit. Is it okay? I spent a lot more time than I thought I would on this, but that's okay. My encoding will become easier. Is it all right? Or have I shell shocked you? Yes, no? Come on, guys. Any feedback? Yes, no?
So one doubt.
Sure, bolo na.
So the middle of the clock is like there is a point in time, right? Where
Middle of the bit, middle of the bit.
middle of the
yes.
bit where whatever is being sent. So like the clock, if it's already out of sync, it is sampling at certain points,
Right,
which may be off.
right.
And like, how does that exactly happen? Like, how does it point out that, okay, like
We'll
this
see
is
in
the point
encoding.
where you should
We'll see in
actually do?
encoding. What I will do as a simple thing, I'll send you a bit transition at the sender's middle of the bit. One simple thing. Okay. So if you thought that your middle of the bit somewhere else, okay, now you get this transition, you say, bring it back there. So you were, according to you, your bit time was here. Middle of the bit is supposed to be here because your 1 millisecond was supposed to be like this. Okay, you're trying to sample in the middle. Note that the receiver is still thinking that is sampling in the middle. It's just that because of its clock, what it thinks as 1 millisecond has gone off. Okay, if you think about your clock, okay, if your clock is slow and you don't compare it with anybody else, you don't know it is slow. Okay, so then what will happen is somewhere the transmitter will see the encoding, will give you, for example, will give you a signal like this. So you were here, okay, and then you are waiting for the next bit interval to middle. So let's say, sorry, you were here, you are expecting the middle to be here. Okay, so if nothing has come, you would have waited till here, but then a transition comes here. So then, no, I think the transmitter is telling me this is the bit. So now I should bring it back here and start counting 1 millisecond from here. Are you with me? Does it make sense?
Yes, that makes sense.
Yeah. So somebody is kind of telling you periodically, this is the middle of the bit. And then you start counting, you bring your, if you thought your middle of the bit is somewhere else, so you're still waiting to sample in the middle of the bit, let's say, or you sample it earlier, another one. you bring it back to that thing, say, oh, start counting from here as the middle of the bit. And then it will count according to your clock again 1 millisecond. I'm not actually synchronizing the per se the actual clocks or something that are used for many other things basically. But I'm synchronizing when you are looking at that bits basically. Okay, so this now gives some other problem. So what if this preamble pattern, post-amble pattern? So say post-amble is the end of frame. Okay, preamble is something. So what happens if that pattern occurs inside your data? So how do you distinguish a preamble from something or a post-amble from something? So you use a standard technique called bit stuffing, which is used in many other cases. So look at this thing. So I have a preamble, which is preamble and post-amble, which is 0, 1, 1, 1, 1, 1, 1, 0. So 0, then 6 ones, then 1, 0. Okay. Now, this is the data that comes from here. Then you have a header. This is the control fields that I talked about. Then this is your data basically. Now look at the data that comes here. Now this actually has 7 ones, not 6 ones. Okay. So I don't really have that 0, 1, 1, 1, 0, but I will not, doesn't matter. So what I will do is this. Okay. Whenever I look for, I'm looking at the bits in the data bits. Whenever I see 5 ones after this, I get this pattern. I don't allow it to go to the 6th one. So I will never allow a 0 followed by 6 ones to occur. Because then I'm in trouble, because the next bit can legitimately be 1 or 0. Even if I stuff anything out there, okay, I will not be able to distinguish. The 7 ones can happen, 0 can happen. So every time I see 0 followed by 5 ones, I'll put a 0 in here. I'll stuff another bit. So here you see you have 0, 0, 0. Then you see 0, 1, 1, 1, 1, 1. I'll stuff a 0 here. Then this 1, 1, 0, 0. Then 0, 1, 1, 1, 1. 1 again, 5 ones. I stuff a 0 in here. Okay. And then I do this. So I have put basically 2 extra bits out there. And then I will unstuff it on the receiver side. How will I unstuff it? How will the receiver know that these 2 bits are to be deleted? Anyone?
In the control field, we can provide information.
No, you don't need that.
After every 5th one, we will delete 0.
Exactly. So, you know, if I see the pattern, not every 5th one only, if I say 0, 1, 1, 1, 1, 1. Okay. I see that pattern. I know the next bit is 0 means because I have stuffed it. Because I would have never allowed anything else to happen. If this pattern, if I look at this pattern, I see this thing, okay, and this 0, then I know that if this pattern is valid, then this must be not invalid. This must be the stuffed bit, because I know what the stuffing algorithm is. Okay. So this is a standard technique you will see not just here, in many other places where you have a pattern that you need to transmit, but then what if the pattern occurs in the original thing itself, basically. Okay, so to summarize before we move on to encoding, okay. So we need the synchronization to know, first of all, we need to know when to start, and then we need to know when to sample. Basically the exact bit duration. The bit duration is known to me, but when to sample. Everybody knows 1 millisecond, but then what is my 1 millisecond and what is your 1 millisecond? So one thing is, let the clock start, don't try to do anything. If you look at asynchronous, I don't try to bring anything closer or anything. So you just start it with the start bit, short thing. So even if it drifts, it won't fall off that middle of the bit too long. Before that, the frame will get over. Next frame, I will again start at the same time because I got the transition to start. Okay. Whereas synchronizers transmission, I basically delineate frames with preamble and postamble. And then I basically assume that the clocks are synchronized and I send a long sequence of bits. Now, to make the assumption work, either I have to send the signal separately, which is costly. So what I do mostly is that in the encoding, periodically I will tell you this is the middle of the bit, this is the middle of the bit, this is the start of the bit. So you know where the start is, therefore you will bring it back. If you thought your start was later or earlier, you will bring your clock back to that start or middle, whatever. Please. Okay. So with that, let's move on to encoding. And as I said, this is just summary. I've already mentioned it. That typically synchronous is much more efficient in utilizing the line. You are using most of the time on the line in sending the data. Even the preamble looks like 8 bytes, and so on. Okay. So if you have a, Ethernet frame, for example, typically your header plus preamble is like, I forgot, 46 bytes or 50 bytes or something. Your header is 46 bytes something. But you can send like a 1500 byte frame. That's the maximum Ethernet thing. There's a few bytes here and there I look up when I teach Ethernet. Okay. So you can even send longer frames with proper encodings and so on. So it also the actual amount of time, the percentage of overhead bits that are not data bits that you transmit, the percentage is much lower in synchronous transmission. So typically, final summary is that most of the computer communication underneath nowadays you will see synchronous transmission. So encoding techniques. So basically says how is data encoded with signals. So we are trying to send digital data. So look at digital data over digital signal, digital data over analog signal. Okay, this is the most relevant one for us, even though this is also important sometimes. So these are things that you already know. We have already talked about it. Digital data, data rate, and so on and so forth. So I'll skip this. So so now we are talking about sending actual signals. Okay. No longer just 0 ones. A 0 can be 5 volt, a 0 can be 7 volt, and so on. So we will not specify exactly 5 volt or 7 volt or something. That will depend on the exact implementation. But so 0 can be encoded with 0 volts, no signal, or it can be encoded with a positive voltage, can be encoded with negative voltage, can be anything. Okay. So that's what I mean by saying actual signal elements, positive pulses, negative pulses, 0 or so on. But not necessarily the amplitude. The amplitude will depend on the circuitry and the exact schemes. Now, looking at the encoding schemes, so these are just terminologies. See, if all signal elements have the same sign, 0 or positive, 0 or negative, okay, only positive, only negative, then we call the encoding scheme unipolar. Whereas if they have more than one, okay, then it's called polar. Actually, polar need not be 2 logic states. Okay, bipolar is 2 logic states. It can be more than 2 logic states also. Duration or length of a bit. So now we are talking actually about the transmitter transmitting. So the duration is what is the time that the transmitter takes to emit the bit. Okay, sort of. So if you look at the transmitter, so transmitter is going to put the signal high and hold it high for some time. Okay, so that is kind of looking at this time that the transmitter is sending the signal. It's not actually taking to emit basically, but how long does it hold the bit out there? And this modulation rate is same as the signaling rate we talked about. I'll talk about it sometime. And these are more historical. These I just put in because the textbook, and I think nobody puts in nowadays. So it has there. You may oddly refer to it, but mark and space was kind of very old terminology to say binary 1 and binary 0. Okay, but let's not do this. So what are the issues in between? These are the 2 major issues. One, we saw the clocking issue. Somehow I want to put that clock inside that thing. Okay. So I want to put this basically. This is one thing I want to do. But then you see, suppose you just wanted to send all zeros. Then your signal would have been like this. Okay, in a normal case, if you don't have to send the clock. But then I know there can be loss of synchronization. So then in the middle, I'll have to send something. Something I have to send to indicate this is the middle of the beat or this is the start of the beat and so on. Okay. So you see naturally that frequency component of this is much less than the frequency component of this. Okay, so I want to send the clock, but then there is a trade-off. If I send the clock, it is possible that the bandwidth that I will need is larger because the signaling rate at which signal changes may go up. Okay, so that is one thing. So I want less high frequency components so that my bandwidth is reduced, but I still want to send the clock. These two are loggerheads. Okay, and the other thing that I want is that no DC component idea. What is the DC component? Remember that zero frequency, amplitude of the zero frequency signal. Why do I don't want DC component? It's more electrical, that you can do AC coupling via transmitter to send the entire signal, okay, so that noise and other things can be kind of interference can be reduced. Okay, so remember, I want lack of no DC component. So this is my wish list. Okay, less bandwidth needed, no DC component, clock sent somehow. Okay, and we'll see that this and this will become kind of a trade-off. Because to send the clock, I have to I have to change the signals. That is the clock. The moment I change the signal, okay, and I have to do it every so many bits at least, okay, that increases high frequency components into the signal that I finally transmit. So I need more bandwidth. These are okay. Cost and complexity is an important issue, and these two are minor, right now minor. Okay, for us, minor issues. Error detection is not primarily what we are looking for here. And signal interference is, again, I told you, deals with the DC codes and so on and so forth. Okay. So the three most important things that I want, that I will look for in encoding in some form: how much bandwidth will it take with the encoded signal as opposed to the original signal? Does it have a DC component? Is the clock being sent? Can it lose clock synchronization? Okay. So with this, let's see some of the things that people talk about. So these are the things that we're going to look at. Non-return to zero level, okay, is the simplest thing that you know about. What we have been talking all along. There's two different voltages for 0 and 1 bits, and it's held constant during the bit interval. Let's say there's one example is that we will follow here. 0 is high, 1 is low. I just did that simply because the textbook follows that, so it's easier for you to follow. We could have very well had 1 equal to high and 0 equal to low. Okay. And then we look at pictures right after this. But see, what is the problem with this? The obvious problem. If you have a long sequence of zeros or a long sequence of ones, the signal level does not change. If it does not change, there is no clock. There's nothing to indicate, because transmitters changing the signal at the beginning or end of the bit interval is what the receiver can pick up to say, oh, this is what the transmitter thinks is the beginning, transmitter thinks is the end. Therefore, I should see count from here that 0.5 or whatever is. But then if I have all zeros and all ones, I get a kind of flat signal. A flat signal, I'm not transmitting that clock from the transmitter to receiver. Okay. So this is kind of can give flat signal, which means very good with bandwidth. Because if I send this, okay, everybody will have to send this. So this will be required anyway. But if I only send all zeros, it will just send this. So bandwidth requirement is good, but may lose clock with long zeros or ones. Okay. And of course, it can have a DC component. Okay, if you send, in this case, you send all zeros, okay, then your signal becomes this. So of course you have a DC component. Inner Zi on the other hand says non-return to 0 inverted on ones. It also has voltage held constant during bit interval. Same as inner Zi. But then that is not, the voltage there is not the indication of whether it's 0 or a 1. The indication of a 0 or a 1 is data encoded as presence or absence of signal transition at beginning of bit time. I'll just have a picture right after this. So basically you say that if I want to send a binary 1, I will make a transition and then I will hold the signal. If I want to send a binary 0, I will not make the transition. Okay. Look at an example, we'll come back to this. So suppose you want to send this thing 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. 0 was high, 1 was low. So inner ZL will send it like this. Okay. Inner Z I says 1, remember this, transition denotes a 1. Okay, that means to send a binary 1, I have to do a transition. Okay, so 0 is here, this bit is 1, I will transition. So it is not the value. Okay, now here is what 0, 0, so no transition. Note that it's not the level because the level is the same for these 1, 0, 0s. But the point is whether there is a transition here that is actually indicating whether there has been something or not. Now there is a 1, I'll transition from whatever I am, I'm going to go to the other level. Then 1, 1, another 1, so another transition. Okay. Then zeros, no transition. 1, 1, another transition. So these are what are called differential codes. Okay. So data is represented by change rather than levels. So levels don't indicate anything. Note that the levels indicate nothing. Here the level is 1, 0, 0. For everything, same level basically. But change in levels is what is indicating that thing. Okay. So you see, if I wanted to send a 1, 1, 1, 1, 1, 1, 1, 1, I would have got a pulse like this. Right? So it's slightly better than inner ZL because inner ZL for 1, 1, 1, 1 will have given you a flat line. Okay. So if you have more ones, you will get more transitions. Each of those transitions indicate to the receiver the start of a bit interval. Okay. And then that basically it can use to synchronize this clock saying, oh, this is what the transmitter thinks is the start of the bit interval. Let me synchronize my clock to indicate that. Start counting from here the bit interval. But then if I send a all 0, okay, I'll again get a flat. 1, 1, 1, 1, 1, 1 is fine. 0, 0, 0, 0, 0, 0. So kind of solve the problem halfway. If you have more ones than zeros, inner ZI improves on inner ZL by putting more clocks out there for the receiver to synchronize with. But moment you have more transitions, your frequency component increases. But it still does not solve the problem completely because you have more zeros, all zeros, more zeros, then you will again get long flat parts where this drift can affect the or the lack of synchronization can make the receiver miss a bit. Is it clear? Yes, no?
Yes, sir.
Okay. So inner Z pros and cons, easy to engineer. It's a very simple code. As I said, makes good use of bandwidth. It presents of DC component. Okay, it will be present in both inner ZL and inner ZI, and not what we call self-clocking. So for inner ZL, long string of ones or zeros. For inner ZI, more improvement, but long string of zeros will still give long constant voltage. I don't want long periods of constant voltage. That is what by saying that there is nothing that the receiver can use to say that, oh, the transmitter thinks here is the bit interval. Start. So this multi-level binary, which is that bipolar thing that I was talking about, this is more than 2 levels. Okay, so this is a little bit strange, but look at what happened. So bipolar AMI says bit 0, no line signal. Okay, bit 1 will be represented by both positive and negative pulse. So both positive or negative will indicate a bit 1. But then I will alternate them in polarity. So what does that first give me? So 0, remember 0 is 0 volt. 1 is both 5 volt and minus 5 volts is 1 1. I'll first put a plus 5 volt and then a minus 5 volt. Okay, so your 0 1 0 1, for example, will be this plus 5 volt for 1, 0 for this, minus 5 volt for this. And another one, okay, plus 5 volt for this, another one, minus 5 volt for this, 0, flat. First of all, what does that give me? Always. Except in one small boundary case, but that can be ignored. Remember my 3 requirements for encoding thing that I want. Low bandwidth, no DC component, self-clocking. Which ones does it give me immediately? Does it give me low bandwidth? Necessarily? Yes, no? So you want to send this signal, not necessarily this 0101 pattern, but use bipolar AMI. Okay, do you think the bandwidth requirement will be low always? Compared to, let's say, NRZL? The simplest code possible. Anyone? So what will happen if I send 1 1 1 1 1? NRZL would have sent a flat thing. Okay, but now first positive, then negative, then positive, then negative, then positive, and so on. And a simple rule, as I said, if you see too many transitions, that means your higher frequency components are high, and therefore you will need more bandwidth. Okay, so this is not, lower bandwidth compared to what? I wrote lower bandwidth here, but compared to what? Okay, NRZL compared to that, it may not be good bandwidth. Okay, but compared to something else, we'll see later, it will lower bandwidth. Okay. Does it have DC component? Yes or no, yaar?
No.
No DC component, except for that very odd case that we can ignore, odd number of ones. Basically, there will be one pulse left, not cancelled, but that power will be negligible. So we basically say no net DC component. Okay. Well, I have written it here. Okay. So you see, as I said, if a long string of ones happen, then there is no loss of sync. But long string of zeros is still a problem. Okay. So zeros mean no voltage here also. Zero terminal I will skip. It's the same as bipolar. It's just opposite. Okay. So bit 1 is absence, bit 0 is alternating positive. The other interesting thing about this is probably the only code that we will study that has error detection. You see, for some reason, if there was a noise, okay, and this voltage there was a spike here, and so this actually, when it reached the receiver, became something like this, and the receiver recognized this as 1. Okay, the lower level circuitry. Then you can easily check that there is an error here, because the polarity of the two ones cannot be the same. It has some, that's why we say there's some little bit of error detection capability also. But not very, important thing for us, right? So we look at one final picture with all the encodings, but let's finish this first. It's not as efficient as NRZ. Okay. Why do we say so? So now you see NRZ and NRZI was using two signal levels. Okay. So remember that Nyquist bandwidth thing, it was n equal to 2 for NRZ codes, both L and I. Here, you are using m equal to 3. You are using a 0, a positive and negative. So theoretically, you could have actually transmitted log to 3 bits of data per signal value. This plus 5 volt, minus 5 volt, 0 and so on. But it bears only 1. Okay, this is not as efficient as this one because, and moment to introduce more than one level, okay, your circuitry becomes more complex because you have to distinguish between more than one level, as simple as that. Okay, more than 2 levels, sorry. So increased complexity, and this is something I have not gone into. It's there in this. We'll not put it in exams or anything, but it will increase. Basically, you will need more signal power to maintain the same bit error probability. The bit error probability is the chance that the probability that a bit will be in error on transmission. Okay, so this is something that you just remember. But it has some nice things. No DC component, so less interference there. Okay. And the last one we do is biphase codes called Manchester and differential Manchester. Okay, was used a lot in Ethernets. Differential Manchester, both. So Manchester, so here the thing is the clock. This transition in middle of each bit period. Okay. But this transition serves both as clock updater. So first of all, there is a transition at the middle of every bit period, both for both of them. Okay. So clocking wise, it's a very good protocol. You will never go out of sync. Okay. Difference between Manchester and differential is Manchester, the clock starts, the transition starts both as clock and data. So low to high represents a 1. Okay. High to low represents a 0. Okay, so if I want to transmit 1011, okay, so you start at low. Okay, so this is my, let's say, bit periods. Okay, go to the middle, go to 1. Okay, then it is 0, so you have to do high to low. Okay, come here, go high to low. Okay, then it is 1. Go low to high. Okay. Now what will happen? I have another one which will require a low to high. So here I have to go low to high, which means I have to bring the signal back to 0. So at the end of the bit interval, I bring it back to 0 and then go here. So now you see, if I get 1, 1, 1, 1, 1, okay. So I always have to go low to high in the middle. I go first one. So this is what I have to go, which means I'll have to bring this down in the beginning. So I'll get basically a very so actually, my signal rate increases a lot. Differential Manchester, we'll just look at a picture shortly, just quickly say. The mid-bit transition, so for Manchester, the transition starts both as clock and data. Whereas for differential Manchester, the mid-bit is only for clock. So you always have it there. Okay. Note that the mid-bit transition may not be there for if you have all zeros, for example, out here. Okay. Sorry, it's okay. It will be there also for this one. So it is for differential Manchester is only for clock. And then transition at the start of the bit represents 0. No transition start of the bit represents a 1. Okay. So I think better to look at a picture. So 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. This is the plain NRZ1. NRZL we have looked at. 1 is transition at the beginning, it's a differential code. 0, no transition at the beginning, so I stay here. 1, transition at the beginning. Then 1, I need another transition at the beginning, so I go here. The levels are not important. Note that 1 for 1, it was high here, low here. But whether I have a transition at the beginning or not, those are the ones. Rest everything is 0. Bipolar AMI, 0 is 0. 1, I first go positive, 0 then 0. 1, I look at the polarity of the previous one. It was positive, so I make it negative. The next one, sorry, the previous one was negative, so I make it positive. 0, nothing. 1, again the same thing. Okay. Pseudo-ternary is just the reverse of that, basically. Manchester, remember, middle of transition, sorry, middle of bit time carries both clock and data. Okay. So clock, so 0, 1 is, 1 was what? Low to high. Okay. So 0 is, so this is the bit interval. Remember, this is the middle of the bits. 0 is high to low. 1 is low to high in the middle, nothing at the beginning. 0 is high to low. Now there is another 0. So I have to make high to low. So I first bring it to high and then go high to low. Same for 1, 1 and so on. Whereas differential Manchester, there is always something in the middle. And this is just the clock. Okay. Whereas the data is transmitted as no transition representing 1. All right. So you see, this was a 1. So there was no transition here. Then this was a 0. So there has to be a transition here. Okay. This is a 0. Another transition has to be here. So you have to bring it out here to make the transition. And then 1, 1, so on, so forth. First transition, no transition at the beginning is 1. So no transition at the beginning and so on. Are you with me? Yes, no?
Yes, sir.
So can I ask something?
Sure, sure.
So in the Manchester and differential Manchester schemes, we use the middle transitions to like synchronize the clock, right?
Right.
However, there are some transitions in both of them, like which are required when we have successive bits which are of the same type, which
Right.
don't serve any purpose in synchronizing
Right.
the clock. So any separate logic has to be built in to determine whether the transition is actually one for the clock or
No. See, you basically, you're on the right track, but let me clarify. It's a good question. So you need the transitions and you need to know when is the transition happening. Okay. See, if I think of a perfectly synchronized clock, okay, then I know perfectly what the beginning is, perfectly what the end is. Okay. So now the middle thing is there always. Okay. Now at the beginning, if something is also there, if I've synchronized my clock, then at the beginning is also synchronized. Okay. And this beginning I'm using to see this transition. Okay. I can also use it as a clock, but if I always have everything in the middle, I don't use it as a clock. I'm looking at the beginning to see, is there a transition? So this is not a sampling of a voltage, this will be triggering something. And if I see the transition, I infer a 1 or 0 according to the code. Okay. So I am not fully aware of your question, but ask me if you don't answer it. So this middle thing for Manchester, differential Manchester, it will work with the clock logic. Okay, I look at the transition and say this is the middle of the bit. The beginning thing, transition may be there, may not be there. If it is there, it will trigger the logic to detect, and then when I detect it, I'll say, oh, this is the one. Its purpose is not for Manchester, differential Manchester, it's not basically to transmit the clock. The clock is transmitted in the middle. But if there is a transition, I can use it, but I don't need to use it. I don't need too many of them, basically. Anyway. Does it make sense?
Yes, like kind of. I just wanted to ask that, like, it cannot happen that it will see the big transition at the beginning as a clock synchronization?
No.
Because it's already
see,
synchronized.
Exactly. It's already synchronized, so it knows it's the beginning.
Okay.
And therefore
Yeah.
it knows that is not the middle. I should not use it basically. Look at that transition and see it's 0 or 1. It will infer the data bit from there. Okay.
Yes, sir.
But then, okay, I'll practice a little bit. So what is the maximum this signaling rate that you need by phase? Okay. So you have 1 in the middle always. Okay. And we have seen for both of them, you may have 1 in the beginning also. There's a bit pattern which is 1 in the beginning also. Okay. So for example, if you look at this one, okay, say 1 1 1 1 for bypass. Okay. So 1 1 1 1. So this thing that is there, this is actually 1 bit duration. Okay. So normally you would have sent only 1 high voltage. Okay. In any other encoding scheme. But now, so basically, if I had 1 1 0 0 1 1 and so on, then I will have something like this. But here you will have 2 of them, then something, then 2 of them, and then something. So typically, basically what is happening is, if you look at this signal, that you are actually within this, whatever was this 1 bit time, you are going to make 1 more transition in the worst case. So that means the signal rate that you require kind of doubles. Because the frequency of this signal is going to be twice the frequency of this signal in the worst case. So it requires more bandwidth. At least 1 transition per bit time. Remember, things like NRZ may not require even 1 transition per bit time. Okay. So you require at least 1. And possibly 2. We have seen this. For the other one, it will be all zeros that will generate that. Pro is self-clocking. It's a perfect self-clocking code. Okay. It has no DC component, almost no DC component, and it has some error detection facility. Because see, the middle of the bit, you are expecting this thing, transition. If you don't see the transition, you know there is something in here, basically. So this is a table that I want you to work out yourself. This is taken straight from Stallings only. Okay. This actually it tells you already, but just work out the things, do the codes, and you will understand the codes out there. So this basically says what is the minimum number of transitions that you can get, okay, per bit basically. So this is the signaling rate, number of signal transitions per data bit. Okay, so we saw that to transmit 1 1 in Manchester, in the worst case, we have to bring it back and do something. So basically, I may have to transmit 2 bits actually. This is the one, this is the one. We have to bring back the signal so I can make the transition again. Okay. So what is the number of signal transitions that you have to make per data bit? Okay. And this is a table that I want you to work out. So minimum for NRZL is obviously 0. Okay. All zeros or all ones, you don't have to make any transition. NRZI also same. Bipolar also same, all zeros. Pseudo-ternary just the opposites, all ones. Manchester is always 1. Okay. You cannot do, you are always making that 1 transition in the middle of the bit. So you cannot go below 1. You can work out what this 1010, the standard pattern, will make. Okay. You will see that this kind of gives you an idea about this one. Okay. And then maximum. What is the maximum number of signal transitions you will make per data bit? So take some data bits. Okay. Look at the total number of signal transition, divide by the number of data bits. You can look at it, infer it actually from 2 bits also, 1 2 bits also. But then, if you look at Manchester, I want you to draw it out and practice it yourself. It all zeros or all ones, but then for differential, only 1, all zeros. Okay. you will still make 2 transitions per one data, because you have to bring the signal back in the middle to make sure that you have to go up. You can go up the next one. So this you work out yourself. So to summarize so far, synchronous, asynchronous, I spent probably a little bit more time than I wanted to there, but it's important to understand what is this synchronous transmission business. Okay, so they understand when we go to Ethernet and all that why you need the preamble. You have to need so kind of visualize things a bit. Okay, so you think of a line. Okay, the clocks are not running at their own rates. I need to bring them together. Asynchronous, I just have to indicate this is the start and this is 1 millisecond. You count 1 millisecond according to you. Okay, but you start counting from the 1. So you were off by a little bit. It's not going to matter. Synchronous, I'm going to say, I will tell you continuously that I'm sending a long sequence. So I want to make sure that you don't drift off or don't kind of fall off that end of that bit, because it's a long sequence and the error keeps on happening. And then when I come to encoding, I'm trying to kind of aid in that synchronous transmission. So that's my goal by doing that self-clocking. But if I do that clocking, one of the other things that I want in the encoding, the signal bandwidth is kind of going to go down. But other performance goes down, you need more signal bandwidth, more bandwidth. And then you have the DC component issue out there. So remember the requirements, practice the codes with some bit patterns, know this min max thing, and do a little bit of your, pros and cons and all those things out there. I know it's a long class, but I will still have some time left. So we'll quickly start on the other one because, we still have a couple of things left. Okay. Yeah, this is good. So we have a trade-off we have seen that biphase is good for synchronization, but needs high signal rate. Non-biphase, lower signal rate, but may cause receiver co-orders. Can we get a good clock synchronization at low signaling rate? Can we get the best of both the worlds? Okay. Now you have some techniques, names here. Before we go in there, can you quickly tell me, do you have any ideas? I know it's tough. It's a long class. We have just got it the first day, but see, the inner Z like codes and all are good for bandwidth, right? So I want to retain that. I don't want too many signal changes. But then they are bad for clocking. They are bad for clocking because, take for example NRZ L, okay? If you have long sequence of zeros or long sequence of ones, then there is a problem. If you had a lot of transitions anyway in the signal, the data that you want to send, sorry, not the signal, the data that you want to send, okay, then you don't have a problem, right? So if I wanted to send 1011001101110, okay, then NRZ is not a problem. I don't need that thing every bit because clocks don't go as we noted. It doesn't fall off that end so soon. I just need some transitions now and then. Okay, what is that now and then don't worry. So if I had this pattern, I have no problem with NRZ. Let's spend a little bit of time on this, okay? We will not start anything new today. But then, if I had 111111 or 000000, I have a problem. Okay? Can you think of anything to circumvent this? So I want to use NRZ, but these things are a problem. So I want to do something so these problems don't happen. Now I cannot change the, I cannot say till the user don't give me 11111. That is not possible. So what can I do? So user has given me all ones. I want to use NRZ, but I want to introduce clocks. Nothing comes free in life. Okay, so you have to give something. But do anyone have any idea about which way to go? Anyone? So obviously I have to introduce some transition somewhere. Okay. So what you do is basically you change the input in some way. You introduce additional bits forcibly, but similar to bit stuffing, you introduce them so that you can detect them at the receiver and take them out before you pass the data on to the user. Okay. And there are two different types of things we do. Just a couple of slides. Scrambling is replace sequences that will cause long spells of constant voltage with filling sequences that introduces sufficient transition. Okay, so if you have 1 0 1 0 1 0, scrambling will do nothing. But if you have 1 1 1 1 1 1 1 1, it looks at the sequence. So that's the difference between this one and the next technique. We'll highlight that. Okay, it looks at that entire thing and it finds a long sequence, knowing the code that you are using. It finds a long sequence that will cause the possible loss of synchronization. It'll change that pattern. Okay, here's an example. Bipolar AMI with 8-0 substitution. I just picked it up because it's one of the simplest things to explain. Okay, so you don't really need to know lots of scrambling techniques, but what you need to know is what is scrambling and what is this XBYB codes and what is the kind of difference between them basically. Even though both basically the goal of both of them is to introduce clocking signals if they are not present automatically in the data. Okay, or I would not say that, just introduce clocking signal. Let's keep it at that. So what it says is this. Remember, bipolar AMI was what? 0 is no line voltage, 1 is alternate positive and negative pulse. Okay, so a long sequence of zeros, basically the line will stay flat, and that is where the loss of synchronization can happen. So what you do is you look at 8 bits together. In 8 bits, if it is all zeros, okay, then what you do is the last voltage pulse was positive, replace it with plus minus, so whatever the voltage is. So if this was the last one, let's say I get 1 0 0 0 0 0 0 0 0 0. 8 zeros after the first one. So first one is positive anyway. So now I look at the 8 zeros, I see there are 8 zeros. Okay, so I'm going to replace it with this. So I'm going to say 0 0 0 plus minus 0 minus plus. So this 8 bit which would have been flat has been replaced by this. Okay, so kind of ensuring this plus minus minus plus, there is at least 2 transitions, okay, in the sequence of 8 zeros. Remember, I don't need to send a transition every bit. I just need to send every so many bits. And this ensuring that every 5 bits or something, I think 4 bits, there is a transition. Similarly, if his last is negative, we will do this 0 0 0 minus plus 0 plus minus. How will the receiver detect? Because he's getting a sequence of voltage levels. How does it detect that this positive, negative, these things have to be replaced with all zeros? Anyone?
There cannot be 2 consecutive positives
Exactly.
or negatives.
Okay, that's where the error detection capability of bipolar comes in. So when it sees this thing, it sees 3 zeros, then it sees this thing, it says, but the previous one was 1. Okay, so this cannot be 1. So you must have scrambled it. Now it is easy. So now start from here, do this 8, replace them with all zeros. Same goes for negatives. The previous is negative, you start with the negative. Okay. As opposed to that, this XB, YB codes, 8-bit NB is an example only. Okay. These are something that they're called block codes. There are many of them, 4B, 5B, 5B, 6B, 64B, 66B. Okay. So scrambling is happening on the bit pattern as you go on, as you encode signal. It's at the plus minus level at there. This is basically at 2 levels. Okay. So first you look at the bit pattern and you encode with another bit pattern. What is that code? You break it up into 8-bit octets. And 8-bit NB says every 8 bits you replace with a 10-bit code. There is a table for that. Okay. And the code is made such, you don't have to remember this, but the code is made such that every 8-bit will be replaced by a 10-bit, which will have sufficient transitions. So you have 8 zeros, they will get replaced by a 10 bits, okay, with some, but there will be some ones, some zeros in the middle of it. And all the codes are distinct. Receiving is easy. You now take out every 10 bits, do a reverse mapping, and replace it with the original 8 bits. Codes are unique for every 8 bit. But you ensure in that 10-bit code, you cannot control what the user is giving you. User can give you all zeros, but you replace it with something which will have transitions in there. Okay. But again, if you think it's a long class, we'll not start anything new. But if you just think for a second, okay, that what you are doing in scrambling and what you are doing in this XPYB code is a little bit different. Scrambling is at the lower level. Okay. You got the data while you are encoding, okay, to transmit it, converting it to signal, you are putting those extra pulses in there. Okay. And you're doing it only if necessary. So only if you get you know the encoding scheme, okay, and only if you know that all zeros, 8 zeros for bipolar AMI, for example, if you see all 8 zeros, then it will do it. If there are no 8 zeros, you will not do it, because you will see at least one transition is there in every 8 bits. So that is fine for you. Okay. Whereas this one is a little different. This you are taking the data and you are changing the code in the first step anyway before you are encoding. And you are adding a 2-bit overhead per 8 bits. That's a lot of overhead. Okay. But you are changing the entire bit pattern with another bit pattern, and then you are encoding it with the normal inertia and so on. So you save on time during transmission, but you are increasing on the overhead more. Because even if a pattern is 101111, you know, which already has enough transitions, you still replace it with the 10-bit code. Whereas for scrambling, you do it only when you need it basically. Okay, I wanted to start error detection today, but it's 9:40. I spent a little bit more time on asynchronous, synchronous than I wanted, but that's okay. So we'll stop here and then you can read this. Yeah, so this is the other issues out there that we are not covering basically. So many of the current protocols, gigabit and all, actually, when you want to go over longer distances or higher data rates, okay. So note that if your data rate is higher, then the pulses are occurring closer together. So that base problem that we talked about, the chance of falling off the end of the bit will occur earlier if the data rate increases. So if the data rate increases, the clocking becomes more important. So you kind of make a trade-off with the header, overhead of putting additional bits and so on. So gigabit, I think, uses, yeah, it uses 8-bit NB. When I do Ethernet, I'll exactly point out. Okay, so we'll stop here. We have Few other topics left out there. So next we'll start with error detection, which will be simple. Just knowing some techniques. They're very practical. So the other thing that I want to point out, I'll point out again at the end. So most of this encoding thing is happening in the hardware lower layer. So again, you need to know the encoding choice when you design protocols and so on a little bit. But again, probably most of these designs will be in the lower layers done by electronics people and so on. But if you do a complete stack design and so on, and you also work in the lower layers, you will need to know them. So we'll stop here. It's a long class. Thank you. So one problem with the 2-hour class is you never get full 2 hours, which is okay. We don't need it. So do you have any questions? These are all there in chapter 5, I think, of Stallings. This first part is mostly going to be very textbook based, but it's important to understand the concept. I don't like putting too many things on the slides, then you just read the slides. And then textbook has a lot of details. You do not need to read all of them. But basically try to, as I say, visualize what is happening a little bit to understand why this synchronous asynchronous business. Why do I need to clock? Why do I need to formalize? Routinely, I found in exams when I asked you slightly twisted questions, checking your understanding, you write the same thing that is there in the textbook and no clear understanding. So go think a little bit. That's my request. Read it, then think a little bit. You have any questions? I'm always there. Okay, so any other questions?